So let us specify in more precise words what we mean by a solution to a differential equation. What is the solution to an ODE? ODE is a common abbreviation to ordinary differential equation. Equation is clear, differential, that means it contains the derivative of the unknown function, and ordinary means it contains ordinary derivatives of a function of one variable, y, as a function of single variable x. As the opposite, we also have partial differential equations, abbreviated PDE, partial differential equation, and a partial differential equation contains partial derivatives of the unknown function, where the unknown function is a function of two or more variables. An example is the Maxwell equations of electromagnetic field, or equation of diffusion, or heat convection, which we will discuss, well, which you will discuss in more detail in next years. But the term partial derivative we will need this term in a few seconds later. So let me talk a few seconds about partial derivative. When we have a function of one variable, say fx is x squared, then we can consider the derivative df with respect to dx as 2x. If we have a function of two variables, say f of x and y being, say, x squared plus y cubed, then for a function of two or more variables, we can consider the following derivative. We observe only one chosen variable, say x, and we consider all the remaining variables, all the remaining symbols to be constant. And then we consider the derivative of this function as a function of one variable. So just something is changing. That means we call this partial derivative. And the partial derivative of f with respect to x is denoted by this funny d resembling 6 in the mirror. And the partial derivative of f with respect to x is 2x when we look at y as a constant. Or, alternatively, we can consider the partial derivative of f with respect to y, where we now, on the other hand, consider x being a constant and y is the independent variable, and then the derivative of the constant is 0, and the derivative of y cubed is 3y squared. No rocket science. So this is the partial derivative of a function of two or more variables. So what is the solution to the differential equation capital F of x, y derivative is equal to 0? By a solution, we mean a function, let's call it phi of x, such that this is true for all x in some interval. Namely f, evaluated at x, for y we write phi, and for y derivative we write the derivative of the solution phi prime of x. And this should be equal for all x in some interval. That means identically equal to 0 for all x in some interval. Not just for one or two special values of x, for infinitely many values x in some interval. An example, consider the differential equation y prime y plus x is equal to 0. And consider the function y is equal to square root of 1 minus x squared. And we want this function to be defined to get real results. So 1 minus x squared must be non-negative, and we want the derivative to be finite, so we want x to be from the interval -1 only. And let us show, well, yes, you may say, how should I know that this equation has this solution? This is not the problem of today. We just want to illustrate what it is, a solution, and what it is not. So I want to show you how to verify, how to check that this function is indeed solution to this equation, and then I will show you some function which is not the solution. So we prepare the derivative. The derivative of square root is 1/2 times the square root times the derivative of the inner function, which is -2x. So on the left, we have y derivative y plus x. Y derivative is here, 1/2 square root of 1 minus x squared times -2x times y, which is the square root, plus x. And if we simplify this expression, then square root cancel, and 2 cancel, and we have -x plus x, which is indeed 0 for all x in this interval. We have 0 on the left, we have 0 on the right, so we see what is on the left is equal to on the right for all x in this interval from -1 to 1. So this function is indeed a solution to this equation. On the other hand, if you consider the function, say y is x squared, then y derivative is 2x, and on the left we have y derivative, which is 2x, times y, which is x squared, plus x, and this is not equal to 0 for all x. Well, there are special values of x. It's easy to see that when x is 0, this is true, this is 0. But we want the left-hand side and the right-hand side to be equal for all x in some interval. Not just for 1 or 2 special values, for all. So this is not equal to 0 for all x. So this is a nice function, not nice enough. It does not solve this differential equation. This function is not a solution to this equation, while this function is.